So last time we were here, we were talking about these, if we have some arbitrary growth function, and remember, like I pulled this out of thin air. I'll show you how we can derive this from actual code, but let's pretend we have this growth function. And we saw that the portion that had like n squared just starts to dominate. As n gets bigger and bigger and bigger, like down this list here, or this table, we see that this column's number grows so much faster than this column's. So much so that the proportion that this column, the proportion that this portion of that expression, the proportion that this takes up of the whole thing gets smaller and smaller and smaller as n gets bigger and bigger and bigger. And if we plot these things, we even see that like, well, 45n, although clearly if this was like evenly plotted, we would see something like this, you know, a nice linear thing. But because of the scale of this, because of how rapidly the n squared portion grows, it looks flat. Like compared to the n squared bit, the n bit looks like it's flat. It looks like it's going nowhere. That's crazy. And another thing too, we even notice that 15n squared and 15n squared plus 45, they're right on top of each other. You can't even tell the difference. They are so close that it really, like this just goes to show that the 45n portion is so inconsequential when n is very large. It's so inconsequential that it like doesn't even matter anymore. So when n is small, which part of the expression is bigger? Well, if we go back to the table, when n is actually really small, we did see that this part was bigger. But again, we don't care when n is small. We care about when n is really big. So as n grows, it becomes bigger. And do the constants really matter? Do they really affect how big the numbers change as n increases? This is perhaps a bit of a perception question about like the math here. But like, if I were to draw n squared and 15n squared is going to look just like this one. Forgive my horrible drawing, but it's going to look just the same. Sure, that coefficient, that 15, obviously scales everything up by a factor of 15, but the growth is the same. And remember, we don't care about like the absolute numbers here. We care about the growth. So although 15 will scale everything up by a factor of 15, the growth between 15n squared and n squared is the same. And that's what's important here. If you're left scratching your head and you're thinking, uh-oh, you know, I was told there would be no math. Well, one, sorry. Two, this is getting more complex until I'm suddenly going to throw away all the complicated bits and simplify everything a lot in a moment. And we're going to talk about computational complexity at the very simple high level in this course. In your discrete math next semester or next year, in your second year computer science, you'll go into a little bit more detail in computational complexity analysis. But here it's going to be high level. So don't worry too much. So yeah, okay. So since n squared, that's the huge part, right? It makes up the biggest part of the whole expression. And because the piece grows as n grows, we say that the n squared portion is dominant. It's the dominating portion of this function. And we don't care about the constants. We don't care about the non-dominating terms. We care about asymptotic complexity, which is really a fancy way of saying, well, the algorithm grows like the function blah, blah, blah. So the time the algorithm takes as a function of n will grow like what? So in this case, I would say, let me clear this again, clear. Here, even though the whole expression, this one right here, this whole expression, I say that this whole expression grows just like n squared. Even though you're like, well, hold on, there's the 15 and then there's the plus 45n. Those things are so inconsequential and don't matter for the sake of how does it grow that we only care about this bit. So we look for the heaviest bit and then we're like, aha, there we go. That's it. Yeah, okay. And this is where we talk about big O notation. So we care about the order of the algorithm. That's like the big O. So in our example, we would say that T of n is big O of n squared. This is big O notation. Putting it all together, the time the algorithm takes as a function of n, in this particular example, will grow like n squared. And we write, so T of n, in this case, is big O of n squared. So, if I have a function like this, say this was my T of n, 17. Let's say, when you're looking at that, and by the way, notice that this is still a function of n. If n is 1, what does that function equal? Somebody type it in the chat. This isn't a trick question. If n is 1, what does that equal? 17. If n is 1 billion, what does that equal? Bingo. No. You were probably looking at the next one or something. I don't know. Yeah, it's still 17. So this function, if we found a chunk of code that happens to have a T of n of 17, that function grows at a rate of 1. It doesn't. I don't care how big n is. No matter what, it takes the same amount of time. It's order 1. And you're like, well, shouldn't it be order 17? Well, no, because we don't care about coefficients. So this is just like a 1. T of n, 20n minus 4. Okay. Well, here, if n is 1, we have 20 minus 4, that's 16. If n is 100, well, that's a 100, that's 2,000 minus 4, 1,996, I guess, and so on and so on and so on. And we clearly see that, like, well, when n grows, this side grows as proportionally to n. It grows linearly. So in this case, it's order n. If we double n, we double the total amount of work being done. Now here we have something that's n times log base 2 of n. Now, raise your hand if you see log and go, oh, no. I don't like these. Because I don't. I don't like logs. So one person's honest, 2 people are honest. Okay, I don't like log. But the good news is, in computer science, when we're talking about log, it's actually a much simpler version of log. It's always log base 2, which is like the opposite of like power of 2s. I'll show you what we mean going forward, but in computer science, we love log base 2 because we're always like having stuff or doubling stuff all the time. So here, I'm gonna clear all this away. If I look at this, I'm gonna boil this down to eliminate all the coefficients. So here's a coefficient, here's a coefficient. So in the end, I have something that's n log times log n. A lot of times we don't even write the base 2 because it's given in computer science, plus n. Well, log, as n grows, if you have something, as n gets bigger, the log of n will get bigger too. So n times log n is still going to grow much faster than n. So this right here has the order of n log n. Here, well, let's get rid of the coefficients. Don't care about the 5, don't care about this thing. So n squared plus n, well, as we saw, the n squared portion, that's going to grow way faster. There we go. And then here we have something that's 2 to the n plus 18n squared plus 3n. So we don't care about that. Well, 2 to the n is going to grow way faster than n squared. Way faster than n squared. So this right here is going to be order 2 to the n. So if I were to plot this, our n squared would be like the flat looking thing where 2 to the n is going to go like this. Whoop, way up really fast. Because that grows hilariously fast. This is actually a really bad complexity. Yeah. So if this is our scale, if these are our axes right here, this is n, and this is, I guess, t of n. if it's something that's order n, it grows like this. If it's n log n, it grows like that. If it's n squared, it grows like that. If it's n cubed, it grows like that. If it's n to the power of 4, it's going to grow like that. Again, pretend that this was a nice line. As these are getting worse. As like we go from n, n log n, n squared, n cubed, and everywhere in between, it gets worse and worse and worse. We want our algorithms that we write, if possible, to have the lowest, the best computational complexity possible. And there's a better one. We actually want something that's O of 1, if possible, and we can have our function be constant time. That's glorious. That's amazing. A lot of time that's not possible, but yeah, like it's impossible to do, well, I shouldn't say that, but well, anyways, we'll carry on learning about this stuff. And you also might think, oh man, how many like different things we're gonna have to know here? There's like n constant log, n log n. Presumably there's something between 1 and n that's just log of n, because log of n grows much slower than n. And is there gonna be like log n times n squared and everything? And yeah, there are, but in general, oh, spoilers. Here, I'm gonna open up this. In general, the stuff that we're actually gonna care about, I think there's a table down here. So here's like a table of like the common ones, but in reality, this is a common one. This is a common one. This is a common one that we'll see at this stage of our careers. This is a common one. This is a common one. N to the power of c, that's like if you have like cubed or to the power of 4. I heard a boop. Can't see. All right, let me zoom in more. All right, well, zooming in, I'm not sure helped a lot. All right, yeah. So order 1 is a common one that we'll see. Log n, that's a common one. N is a common one. N log n is common. N squared and n to the power of c, we can kind of think of these as like the same-ish because c can be like a 2, a 3, a 4, or whatever. C to the n, this is exponential. That was like 2 to the power of n. This is a really bad one. And then there's n factorial, which is hilariously bad. This is like the worst you can ever find. And we'll talk a little bit about this. But in general, the ones we're going to look at are going to be few and far between. You're not going to need to memorize every possible combination of n and logs because we're not going to talk about this at this stage. Every once in a while, maybe I'll try to throw you a curveball or something, but I'm not going to try to be overly mean. So let's have some fun. Let's quiz. What is this one going to be? This is big O of what? Someone type it in the chat. Let's see. What do we got? N squared. Yes, n squared. N squared. Yeah, everyone said n squared. Fantastic. Why? Well, because n squared grows a lot more than this bit. Okay. So now we have n cubed plus log base 2 of n minus 4. So what's this one going to be? N cubed. Absolutely. N cubed. Because n cubed grows a lot faster than log of n. And if you don't believe me, Google's an amazing thing. Because it even lets you, I don't know if you know this. Let's like plot n to the power, where's the power of? 3 and log base 2 of n. Oh, come on. Maybe I have to do x's. There we go. So look at this. Log base 2. Look at this. It's like flat. Like clearly it's growing if you zoom in really far. In fact, let me zoom in. If we zoom in far enough, we'll see that like, okay, yes, the log base 2 of n does grow, but n cubed grows so much faster. And again, I realize this might be hard to see, but point being, n cubed way worse than log base 2 of x. All right. Oh, no, don't look at the answers. Don't look at the answers. All right. Log base 2 of n times n plus 5. So what's this one going to be? N log n. Absolutely. You know that because you know that, not because you saw the answer, right? Right? And now we have n squared plus n cubed plus 3. What do we say? Yep, n cubed. Now this is a funny one because, well, 2 to the n versus n to the 100. Whew. What's the dominating bit? 2 to the n, yes. Now, to be clear, in practice, with n's that we can think of in our universe that, like, this will probably appear worse. But, yeah, and this right here, I don't, you would have a really hard time finding an algorithm that's not deliberately designed to be horrible that looks like this. Oh, okay. So how do we get t of n in the first place, though? So this whole time we've been talking about t of n. We've been talking about, given some growth function that we magically obtain somehow that's representative of how an algorithm runs, how do we take that t of n to get to our big O of n? Which was actually pretty easy, right? It was just like, okay, just look for the dominating thing and there it is. How do we get t of n, though? Well, we look at the code. So whenever we see a statement, whenever we see like one line of code, how much stuff is being done there? Well, for example, now, don't get me wrong, one line of code might be a function call to something that's very complex. But just a statement like this, that's like one thing. That's two things, that's three things. Okay, so this would be like t of n equals 3. Okay, I'll call it 3. Maybe this takes a couple of steps inside the computer, but I'm just gonna count all those steps as taking the same amount of time because I'm lazy. Either way, this is t of n of 3, which is big O of 1, right? Oh, look at that. I didn't need to draw it because I already wrote it. Cool. Now, loops. You're going to want to look for loops because loops are where things get interesting. The number of time a loop executes can sometimes depend on some value n. Have a look here. How much work is being done by this code? Well, inside this loop, we have something that's like order 1, right? It's t of n of 1. But we're saying run this code how many times? Well, 0 to n. And I don't know what n is. So it looks like I'm running this thing that takes 1 unit of time n times. So this is like t of n is equal to 1 times n plus, and I guess we have this one step up here, plus 1, which of course is big O of n. Oh, I already draw it, and I have a feeling I have it in there. Yeah. So what I like to think of is like, how much stuff is being done here? Well, the I is going to be 0, then 1, then 2, then 3, then 4, then 5, to n minus 2 to n minus 1. What about checking the bool and increasing it? That's okay. Then we can, like, if we want, we can say that's like, oh, maybe that's like, okay, checking that condition. Maybe t of n should have been like 4 times n. But at the end of the day, when we're only really looking to get the like something in terms of big O, I'm gonna be lazy and just ignore all that. Yeah, it's just order n still. So you're absolutely right. That would take up more time, and we should count that if we really cared about getting t of n. But we don't, at this stage, we don't care about getting t of n. Really what we want to do is go to big O. And sometimes going to t of n then to big O helps. But those nitty gritty little details about like, well, you know, we're checking that condition and then we're adding 1 every time. That's like 2 more steps. You're right, but we can ignore them because ultimately we know we're going to big O. So you're absolutely right though. Good observation. Now, let me ask you something. Here's a quiz. This is a really good quiz. And if you're right, I'll give you a thumbs up. That's what your reward is. Imagine let me erase everything. Whoop. Nope. Imagine I came here and wrote this as not n. It's not based on n. It's 1,000. Actually, let's make it 1 million. Well, I is less than 1 million. Can anyone tell me what the computational complexity of this is? What the big O is? If this is I is less than 1 million, what is big O? 1. Haha, I tried to trick you. So I owe you a thumbs up. Congratulations, you were right. The reason it's still 1 is because this function here does not depend on the size of n anymore. It doesn't. This loop is always going to run 1 million times. So our t of n, and let's get precise like we were suggesting. Okay, we're doing this one step here plus the comparison plus that. So that's like 3. It's going to be 3 times 1 million plus 1. Well, that ends up being 3,000,001. Well, that's just t of n equals 3 million. Let's say roughly equals because I'm lazy. Is that, which then just gets down to order 1. And if you're saying, but hold on, if we grew n before, you said like it was, it was linear. You're right, but here we threw away the n and we made the n some constant value. No matter what n is, I is always, like that loop is always going to run 1 million times. So I tried to trick you, but you're too smart. So well done. Yeah. Okay. Nested loops. This is where things can get hairy, but like everything else in the course, there's no trick to this other than what are the rules? Just follow the rules. So let's say this is my code. Okay. So this right here is like 1 step, right? And I'm running this how many times? N. So this is like n times 1, right? And then this is 1 step. So this is like 1 plus everything here is like 1 plus 1 times n, right? And then how much is this part being run? Well, n times. So that's like n times 1 plus, I'm just going to do the n because I'm lazy, and then plus 1 because we've also got this thing here, plus 1. So at the end of the day, let's expand this out. We have t of n equals roughly n plus n squared plus 1. Well, I mean, that's big O of n squared. So here we had a nested loop. And once we do the analysis, again, no trick, just what does the code say? We can still get our big O, n squared. A lot of times when you see nested loops, your brain will go towards, is it like n squared or something? And we can visualize this as, well, this inside loop is going to run 0 through n, right? So it's going to run n times. But how many times is this inside loop running? Well, n times. So we do this another n times. So it's like a square. Look at this. It's literally a square. Ooh. So we have a square and big O of n squared. Wow, that's fantastic. How about that? If you're wondering, how do you know when it's like here, somehow I magically knew that this should have been addition and then this should have been multiplication. Again, you're probably looking for a hack and a trick of like, how do I know when? The trick is just, if it's nested inside something, it's probably multiplication. If they're like subsequent, if it's this line of code followed by this line of code, it's probably addition. And then this part's nested and then this is subsequent, so it's probably addition. So that's how I know. Yeah. Okay, look at that. Hey, fantastic. So test. Ooh, okay. All right, here's a good one. Okay, don't type the answer into the chat right away. I want you to think, and I gave you this kind of like line chart here to help you visualize. What is the computational complexity of this? Big O of what? So don't type it in the chat. I want you to think, and I'm gonna give you a second. What time we got? 1:50. So I'm going to give you a second to think about it, and we'll see how you do. I'm gonna keep on my other computer. I'll keep an eye on the time. If you're trying to come up with an answer immediately, you're not doing this the right way. You got to think, well, okay, look, I know this is 1, so we can, whatever, and this is going to be a +1, so who cares? But the question is, how many times is this loop going to execute? Well, it's going to run for when I is 0, and then it's going to increment by 2. So it's not going to run for when I is 1, but it'll run for when I is 2. And then 4. And then 6. And so on. So, how many times will, and you know what, for simplicity, let's assume n is a multiple of 2, because odd numbers suck. How many times will this loop run? Now someone type it in the chat. So you're both right. So the number of the answer to the question of how many times will that loop run is half of n, 0.5 n. Which then, do we care about coefficients? No. So it's still big O n. So you're both right. So because this right here has a t of n that comes out roughly to, I guess, 1/2 n plus 1. We don't care about this bit. We don't care about this bit, so it's O n. Now here's the really tricky one. This one, I'll give you a second to think about. I'm going to warn you, it's tricky. A lot of you probably aren't going to get it. I know I didn't when I first saw it. Now I know because I'm just used to it. But the trick with this one is, how many times will, like, if n, it can be an arbitrarily large number, but n is a fixed size. So how many times is that loop going to run? I'll give you a second to think about it. For those of you that don't know, this means like double I. And you'll notice that I starts at 1 because if it started at 0. So this should go 1 to 2 to 4 to 8 and so on. N to the power of a half. So you're thinking like root n, eh? Log n, square root n. So those are classic guesses. The good news is half of you are right. 1/2 to the n? No. Order n? The answer is log base 2 of n. Now, why? Well, first of all, this is doubling every time. So your mind should be going like, oh, if it's doubling every time, that's like n to the power of 2, right? Or no, no, 2 to the power of n. But we're growing at a rate of 2 to the power of n, where n is some fixed value. So let's say, for example, n is 128. So how many times would this loop run? 1, 2, 4, 8, 16, 32, 64, 128. And I guess maybe less than or equal to. So when n is 128, we run 1, 2, 3, 4, 5, 6, 7, 8 times. Okay. What if n was 256? And I don't know, I'm just pulling these numbers out of thin air. I don't know, there's no pattern. If n was 256, how many times would this loop run? Well, 9 times, right? If n was 512, how many times would it run? 10 times. So what's the relationship here? What's the relationship between 128 and 8, 256 and 9, 512 and 10, 64 and 7, 32 and 6, and so on? What's the relationship between, I know it's probably hard to see, it's getting all jumbled. Ugh, now it's even worse. What's the relationship between the number of times that loop's running and whatever n is? Well, let's see. For some reason, I have an inkling that it is what I already said it was. Log 2 of 128. 128, well, I guess it was 7, so what's up there? You know why it's 7 and not 8? Because I was saying pretend it's less than or equal to n. I should have been saying less than n. So if this was less than n, not less than or equal to n, we would run 1 less time. So the relationship here is the log base 2. 256 one more time. And 512, one more time after that. So if you're asking yourself, why is he doubling those numbers every time? Well, because it makes for easy math. And two, I mean, here we are, here, let me clear everything. Oh. Okay, I don't know why I can't delete that, but here we're doubling every time, so whatever, easy math. That was a tough one though. Stacks. Now, we saw two different implementations of a stacks, and stacks are pretty efficient in general, but which one's better? When we pop something from a stack, what's the computational complexity? Have a look at this code and someone type it in the chat. What's the computational complexity of popping something from a linked stack? Any ideas? N? Popping one thing from the stack, you think it's N, huh? It's 1. It's 1. Why? Well, because if the stack, I mean, the stack might be size N. There might be N things in our linked stack. But to remove this one thing, all we have to do is get the data out of it, delete it, and return it, you know? So it's order 1. Similarly, pop from the array int stack, it's the same thing. It's order 1. So it looks like both implementations of pop, whether it's the array stack or the linked stack, is order 1 for pop, which is fantastic. And if we have an algorithm that's order 1, that's exceptional. That's awesome. But push. Here's the linked stack. What's the computational complexity of pushing something onto the linked stack? Someone type in the chat once you know. 1. Absolutely. It's still 1. Why? Well, because all we have to do is make a new node, put the data in it, set its next to the top, and then update what top is and increase count. Those are all like 1 unit of time, let's say. This right here, all of this work does not depend on the size of the stack at all. So it looks like when we push onto a linked stack, it's order 1. That's fantastic. Now we've got an interesting situation. How much work is being done on push for the array stack? What is the computational complexity here? And this is a tricky question. There's a bit of a trick to it, because we got to know what's going on in expand capacity, because expand capacity looks like this. And top is our stand-in for n. So top is equivalent to n in our situation. So we might have to expand capacity. So how much work is push in an array stack? What do we think? Someone try. Someone give it a guess. Order n if you have to expand capacity, 1 otherwise. And okay, so you're all right in your own way. And you're also, and Felix and Alex, you're also wrong in your own way. So Cole is right in that if we have to expand capacity, it's an order n operation. Okay, if there's n things in the stack, we got to copy all n things over to the new array. But if we don't have to expand capacity, it's order 1. That's fantastic. Now, you might be thinking that it should be n though, because we always, like when we talk about computational complexity, we often think about worst case scenarios. And this expand capacity is the worst case scenario. And you're right. But this particular scenario is a very, very, very special case that is, the analysis of this is well outside the scope of this course. But I'll tell it to you anyways, and we'll end on this, is we call this an amortized, we can do an amortized analysis of this, because this expand capacity gets called so infrequently. In fact, if I have an array of size n, and it starts as empty, how many times can I push something onto this stack before I need to do an expand capacity that takes order n time? It's not a trick question. How many, if we have a stack, if we have an array of size n, and there's nothing in it, how many things can I put into that array? No, we're not talking about default. It's just some arbitrary size now, n. N could be 10, but let's pretend it's size n. How many things can we put in that array of size n? N, exactly. If it's size 100, we could put 100 things in it. If it's a size 1 billion, we could have 1 billion things in it before we have to expand capacity. So we actually get n order 1 operations before we have to do 1 order n operations. This is the order n operation. And what we'll often do is we're like, well, you know, we can kind of take all of this work here, the fact that we have 1 ordered n operation, and amortize. We can spread out, we can think of the total work being done as spread out over all of the previous n calls. Because we can kind of think like, well, what if like we were like, well, ignore this, and just if we divide this n among the n things before, this could be like 2, which is of course still 1. So that's like a neat, looks like a mangled stick person, probably. Poor guy. Point is, this is actually, worst case scenario, we know it's order n, that's actually bad, but really a lot of the time it's order 1. But if you have something that's order 1 and something that's order n most of the time, or pardon me, if you have something that's order 1 and something that's order n every once in a while, we know that's still going to be worse, right? So which implementation would you want to use? Would you want to use the linked implementation or the array implementation? Any ideas? Linked. Why? Well, because it's order 1, right? It's always order 1, where that array 1, every once in a while, it has to do the expand capacity, which is bad. Here's the funny thing though. In principle, you're correct. In principle, in terms of how we're defining computation and what the rules are, you're absolutely correct. In practice, and this is an important thing to consider, in practice, these computing machines that, like I'm hitting my laptop, these computing machines that we use, they work in such a way, they are engineered in such a way that actually in practice, the array is always going to be faster. Always. Even though it will still have that order n thing, in practice, the array is always going to be faster just because of how these computers work and the indexing of RAM and whatnot. So in principle, on a purely abstract mathematical definition of talking about these algorithms, the linked implementation is arguably the superior one, unless we consider amortization, but really we know that linked one seems to be kind of better. But in practice, we have that the array ones are actually going to be faster. Now, I really do want to say though that really when we do incorporate amortization, the array one is still order 1. We would still call it order 1. It's amortized order 1, but you'll learn about amortization next year. Let's see, was there any other slides? Which has better complexity? Awesome. Okay, perfect. All right. So that's it for today. I will see I'll see half of you tomorrow, and I'll see everyone else on Friday, and try to, like I was saying earlier, acknowledge the difficulty of this year. Try to take your breaks when you can, and take it easy. I'll see you later. Enjoy the rest of your day.